you've ever wanted to use machine learning for algorithmic trading, I'm going to show you the basics you need to get started in this video. So first, we're going to talk about linear regression. It's the most core and essential model you'll ever need to know. Then we're going to talk a little bit about ridge regression, which is a variation on linear regression that improves some common things that go wrong when you use it. And then finally, we're going to look at boosting techniques, which are a bit more advanced, but also a bit more useful for live trading. First, let's talk about some important points though, because before you dive into machine learning, these are some things that you need to understand, and they're things that people don't really talk about that often either. First of all, when you think about machine learning in the context of algorithmic trading, you need to understand that it's just a tool, it's not an edge. So if your strategy is not already profitable, then adding machine learning is not going to make it profitable. And let me give you an analogy. Let's say that you are somebody who owns an e-commerce website and you spend all of your time messing around with the color of your checkout button. And you find that by tweaking your colors just a little bit, you increase your checkout rate or your click-through rate by 2%. But at the end of the day, your product sucks and nobody likes it and your customers are all unhappy. Well, you're totally focusing on the wrong thing. So something to keep in mind here, this machine learning is going to be an optimization tool. It's not going to be a successful strategy in and of itself. Another thing to remember is that simpler is going to be better for live trading. So I'm certain that there are people and teams out there that are using deep neural networks and reinforcement learning for trading, or at least trying to make that work. But as a day-to-day practitioner, I don't really mess around with any of those things. They're very difficult to understand. They're very expensive to run, the time it takes to train them. And in practice, simpler models just tend to work better. So something to keep in mind, don't necessarily look for the most fancy techniques right off the bat. Today, we're just going to talk about 3 of the most simple and basic techniques that are actually useful for live trading and research as well. And that's my last point, is that machine learning, you should think of as both a tool for your research process and your optimization process. So when you're just developing your strategy, you can use machine learning and tools like linear regression to understand your data better. And then once it's time to go into live trading, you can use machine learning to optimize your weights and how you ultimately combine your signals into a prediction or a forecast that you're going to make trading decisions based off of. By the way, if you don't know me, my name's Ben. I'm a systematic trader and software engineer who manages his own portfolio of systematic trading strategies. I also talk about it and teach it here on this channel, so if you're interested in that, make sure to subscribe. And then finally, I will have a link in the description where you can grab the code from this video and other free resources as well. All right, with that said, let's jump into the coding notebook. So first up here, I want to talk about simple linear regression. And this is going to be your most foundational and basic tool that you'll ever need. If you're not familiar with simple linear regression, I'll give you just the basics. Now, this video is going to be focused more on how to use it in a trading context, but the basic idea is that you have 2 variables, right, x and y, and they have a linear relationship between them. So you can actually predict y from x using this formula, y equals mx plus c or plus b, like you know from algebra class. Now, the objective of linear regression is to find this best fit line given the relationship between the points. And I'm going to show you how to compute that in 2 different examples here. So the library that we're going to be using is called scikit-learn. This is probably the most useful machine learning library you'll have. It's very easy to use. It has a standardized interface, and it gives you models out of the box for classification, regression, clustering, as well as some pre-processing utilities and different features and functionalities that are going to help you develop better machine learning models. And it's completely open source and free to use. So this is going to be the simplest tool for machine learning in Python. So the first example that I want to show you is how to compute a simple regression on price data. And if you're watching this and you're a little bit more experienced, you're probably thinking, why are you doing this on prices? Maybe you understand why. It's not a very realistic thing. Normally, you're not trying to forecast price as a trader so much as return. But here it's going to give us a nice linear relationship. So I just want to demonstrate this as an example where everything is going right. So very first, we're going to have our standard imports. So we're going to use NumPy and Pandas for our data handling. And we're going to use Yahoo Finance for actually collecting the data. And then Matplotlib will help us with some visualizations. Then you'll see here that I'm going to import this linear regression model from sklearn. And I'm also going to include some metrics here like the mean squared error and the R-squared score that will help us evaluate the quality of the model. So I'll download our price data just for a single stock from 2010 to 2024, and we get around 3,522 rows. You'll see we have just our open, high, low, close data on a daily cadence. And then the simple variable that I'm going to use here is just the price yesterday. So we'll look at today's close price, and then we'll actually just shift it 1 day over to get yesterday's close price. And then after I do that, I'm going to drop the null values off of the data frame because that will create 1 row where there are null values. Then what I'm going to do is actually take the x variable and the y variable and store them in variables called x and y. And these are what we're going to pass into the machine learning model, the linear regression. Now, just a quick sanity check. If we scatter plot these variables out here, you can see that there's a very tight linear relationship here, right? And that's completely expected because yesterday's stock price is going to be very close to today's stock price, unless there's extremely high market volatility. And even still, you're not going to have that over a 15-year period. So it's not surprising we see this relationship. Then we're going to split our data up into training and testing sets. There is a utility function you can use for this in scikit-learn, but I'm just going to do it manually here because it's not very hard. And then I'm going to define my model. So this is how you would do this in sklearn. You would say, create me a new linear regression object, and then you just call the fit function on it using the X training data and the Y training data. And you see it returns to you this linear regression object. And finally, once we have that, we call predict on it using the test data, and we get our ultimate Y prediction. Okay, so it's pretty simple, right? We just define the object, and you can replace linear regression with logistic regression, with anything you might be interested in. You just define the object for the model, you call fit, passing the X and Y data, and then you call predict, passing the test data for your X variable, and you get your forecast. Okay, now let's evaluate the performance of it. So here I can use these utilities, mean squared error, R squared score, and mean absolute error to see how the model did. And you'll see right away that the R squared of 0.98 indicates that this model is a very good fit. Basically, the closer this is to 1, the more your model is capturing the linear relationship here. Now, the mean squared error looks a little bit high, but keep in mind that this is in dollar terms. And the mean absolute error here is about $2. So that's basically saying over the values, the range of values that Apple's price takes, the absolute error on average is just $2 between the real value and the predicted value. Now, finally, let's plot this out. So now instead of plotting X versus Y, we're going to scatter out our test data versus the predictions that our model has come up with. And we're also going to get our coefficients, the M and B, right? Or here it's M and C. But we're going to get these coefficients so we can actually plot out the best fit line that we've designed. And finally, we'll see here that, again, it's a very clear linear relationship, and that our red line here, which is our forecasting model, is a very good fit to it. So this is kind of a deliberately easy example just to show you the process, right? Where we're taking our initial market data, then we're defining our X and Y variables, creating a linear regression object, and then ultimately using that to fit and forecast on our data variables. But in practice, nobody is actually doing this on price. So what we're going to do instead is forecast on returns, because we want to know what the direction of the market movement is, right? We want to know if we're going to bet on a stock today, we want to know what it's going to do tomorrow in terms of going up 2% or down 5% or up 8%. That's what's really interesting to us. So let's take this same model now and repeat it on returns. So what I'm going to do is just re-download my data frame, my DF here, so it's kind of refreshed and it doesn't have any variables on it. And what we're going to do is we're actually going to use the lagged returns now to forecast the next day's returns. So you would consider this an auto-regressive model if you're going to use the fancy term for it. Basically, you're trying to predict tomorrow's value in terms of what happened today and yesterday and the day before it, so on. So here, I'm just going to use percent change to calculate my returns, first of all, and then I'm going to shift those values 1, 2, and 3 days to get my different lagged returns values. And now you can see the data frame here has these different columns in it for the returns. And obviously it introduces some NaN values because when you lag the data, you don't have the values for the days before the lag happened. So we're just going to drop out those null values again. And now we have a nice clean data set with our corresponding variables inside of it. Now this time we're going to actually do what you would consider a multivariable linear regression, in the sense that there's not just one variable here, there's not just one independent variable that we're trying to use to predict the dependent variable, but there's actually 3, right? So it'll work all the same. We'll just define our X in terms of those 3 variables here, and our Y, again, will be the next day's returns. So we'll shift that over by 1, and we'll drop the missing value, of course. And then finally, we can do our train test split, define our new model with the training data in it, and then predict the results. So now let's take a look at the results here. And in terms of the mean squared error, you can see it's very low this time because, right, we are in return space, so the daily returns are going to be a much smaller value. But our R squared is now negative 0.002113. So what does that mean? Well, I told you before that an R squared of 1 means that our model is a very good fit for the data. And an R squared of 0 or negative means that we are not fitting the data at all. So now if we actually plot this out and see how it looks, here is the result in terms of the return space. So if you look at the returns, I mean, this is not a linear relationship at all. I mean, it's just completely scattered. It's almost random. It's almost noisy because there doesn't really, we're not capturing any relationship here. And if we look at this red line, I mean, it's directionally correct in the sense that it's horizontal through kind of this core central cluster here, but there's so much variance in the model that we're not ultimately predicting anything. So this is kind of a limitation of linear regression here, first of all, because there's clearly not a linear relationship that we're modeling, but also our simplistic feature design is just not going to be significant enough on an instrument as liquid as Apple, right? There's so many different features and things that are going into that stocks, returns on any given day, that simply looking at the previous day's returns or the lagged few days returns is not going to be sufficient to create a forecasting model off of. So that's your first lesson here. It's a lot harder to do this thing in return space, but that's really the goal of what we're trying to do in the first place.
Yeah, so our next model is going to be ridge regression, which is another variation on linear regression that
helps you avoid overfitting a little bit. And if you're not familiar with that term, overfitting is basically when your model learns a little bit too much from the past data in such a way that it doesn't generalize to the future data. So this is a very common problem with financial data where there's not a lot of signal and there's a lot of noise. So it's something that we often have to deal with and correct. So I'll show you the quick mathematical background here just to show you what we're going to do so you get some sense. But honestly, this example is more about how to use the same setup that we just saw with linear regression in terms of the code structure and just swap out different models and see how it all works the same. But just so you know some of the background here, if you're not familiar with ridge regression, typically when we do a linear regression, we are trying to minimize this quantity here, the sum of squared errors. So when you were looking at that line graph earlier and you saw all the different data points, basically what this term on the inside here is doing is measuring the distance between our line and those data points and trying to find a line that minimizes that distance across all of the different data points. Now, what we do with ridge regression is we basically take this exact same equation here, right? So these are the exact same thing, but now we add on this additional term here, which is a penalty term that you would call the L2 norm in technical terms. And what this is doing here is this beta, this value here, is the coefficient that we are finding for our linear model. And what this is doing is it's trying to reduce those values of beta so that they don't get very large. And that basically is going to normalize them and kind of keep everything contained so that it doesn't overfit as badly, basically. So that is the core idea behind ridge regression, is that we are taking our same least squares method here, and we're adding on a L2 normalization term to help it shrink those coefficients in accordance with this parameter here, this lambda. So if that math doesn't make too much sense now, don't worry about it. This isn't really a ridge regression 101 tutorial. It's more just how to use it in Python to improve your modeling. So what we're going to do to actually run our ridge regression is just first off import it from the sklearn linear model module. And then here I'm just going to use some synthetic data. So we'll have some random variables. And I'm going to define both my linear regression and my ridge regression. So you'll see here that I'm setting my alpha parameter equal to 1. Alpha is this lambda here. Okay, so it's the regularization amount. Basically, the higher this value is, the closer our coefficients, our betas, are going to be to 0. So here, if we run this, if we look at our coefficients, you'll see we kind of get what we expect, right? The regression coefficients are slightly larger than the ridge coefficients. So it's just adding some regularization into this, kind of shrinking these values and making it a little bit more stable and, again, a little bit less overfit. If we plot this out here, you can see this result visually, right? Pretty much all the orange dots are smaller than the blue ones. Now, this isn't a super egregious example, right? You can imagine that if you had multiple features or many, many features and they were all correlated to each other in some way or another, then you would actually want to shrink your coefficients quite a bit, especially on those features that are a little bit duplicated, because otherwise you would be overfitting, you'd be capturing too much information in the model. But this is just an illustrative example. Yeah, the main thing you will notice is that our setup is exactly the same. We just import the ridge object from the library. We call .fit, passing in the data. And then eventually we come down here and don't actually do it in this example, but we would call predict exactly the same as before. So now I want to show you an example where we actually take this and move away from synthetic data and use real market data. And now the objective is going to actually be to model the relationship between volatility and volume. And that's going to be a more natural relationship. You can imagine that the more volume there is, the more volatility there is, and vice versa. So we'll use our Apple data again over a 4-year period. We are going to use this train test split function to divvy up our data set into training and testing data sets. And an important thing we're going to do here is we're actually going to scale our features down before we pass them to the model. And the reason for that is because ridge penalizes these large coefficients. Well, we want to make sure that all of our features are kind of at the same normalized scale so that if one just has a higher magnitude than another, it doesn't get a much larger coefficient in order to compensate for it. Finally, we're going to define our ridge model, call fit on it, and then predict. That's what I was referring to earlier. We just use the same setup pretty much every time. And lastly, we can look at the fit of this line down here, where we're just going to see, the scatter plot of our volatility versus volume, and we get a nice linear model between here. Now, we could have just as easily used linear regression for this. This is really just another example of how to fit a linear model. But if you're ever struggling with, an instance where you have a model that's very overfit, or where your coefficients are kind of blowing up, or you have multiple redundant features, things like that, it's worth it to consider using ridge as a way to possibly solve that. You can also use lasso, which is a form of L1 normalization. But again, if you're not so familiar with these, if you're just a beginner to machine learning, don't worry too much about it. This is just another tool in your toolbox. Real quick, guys, before I go into the third and final example on gradient boosting, I want to just remind you that if you want to grab any of the code from this video, it will be posted here in our free community, school.com/algos. This is where I host all the code from our YouTube channel, as well as some free courses that you can take on Python Foundations, as well as get access to our bot building challenge, where we help people build their first trading bot in 1 week. So if you're interested in that sort of thing, like I said, go to school.com/algos. It'll take you 30 seconds or so to join, and I hope to see you there. The third and final model that I want to show you guys today is XGBoost. And This is going to be a more advanced model. It's better for higher dimensional data. And to be honest, I'm not going to get into the whole derivation or background on it because it's a little bit more complicated than the other ones. What I will say is if you're interested, I would recommend going to their documentation and clicking on this Introduction to Boosted Trees article. And then you'll get a very good background and some context on how exactly this model works. But again, this is a little bit out of scope for us today. Today, I just want to show you how to use it because it's usually one of those things where I will just try it out if I have a bunch of signals that I want to combine. Oftentimes, I get a better result using XGBoost than I do just with a simple linear model, especially if I don't expect the variables to have a linear relationship between them. So let me show you how to use it. So now we are not using sklearn anymore. We're actually using this XGBoost package, and it's pretty simple to install. If you are using Google Colab already, then it's just installed for you out of the box. And the key takeaway here is we're actually able to use the same utilities from sklearn. So for example, like using this train test split model, and then even the same interface, just with a different library. So we're going to define our XGB regressor object, and then we'll call fit on it, and then we'll call predict on it. So it's really, really simple to do, guys. That's one of the reasons that we love Python so much, is because you kind of have a very simple 3-step process for any sort of machine learning thing you might want to do, and it just works. So here we can actually use this trained model to get a sense for what features are most important, or which ones are kind of explaining the most, of the result according to the forecast. Now here it's just random noise, so it doesn't really matter. But let me actually show you a slightly more realistic example, and I'm going to put realistic in air quotes here. So let's say we have a data set with a bunch of features on it that we expect to be predictive of future stock returns, right? So you would consider this an alpha signal. Here, I'm going to create a bunch of these. Now, these are not going to be anything revolutionary, especially considering that with Apple, with any sort of liquid stock like this, most of these features are going to be very publicly accessible pieces of data, and therefore they're either already going to be incorporated in the price of the asset, or other people would just be trading them. So it's not any unique alpha here, but these are the kinds of things you might think about, right? So for example, we can look at its previous close, change in volume, the change in close price, so that'd be like the returns. We can look at a moving average, we can look at the RSI indicator, and we can also add in more things, right? Like MA10, MA50, 200, some EMAs, MACD, ATR, and all these different indicators. Basically, I've just added a bunch here to show what a high dimensional data set would look like. We'll look at lagged returns, we'll look at log returns, we'll look at volatility, and then we're going to pass all of these things into our X, input variable here. So now we have many more features as opposed to just one or two. And part of the idea is that as we have more features like that, in this case, a lot of them are going to be very related to each other, right? For example, the moving averages over different time periods, those are going to be pretty correlated to each other, and the same with the EMAs. But anyway, the point is just to show you an example of a higher dimensional data set. And I will leave it up to you to do your own alpha research because that's really where the money is. But anyway, here we can take this, and I'll just show you the result of training both a linear model and a XGB model on it. So you can kind of see the spoiler already at the bottom. Let me rerun it just to see the data fresh. But again, the key takeaway here is that both models have the same interface in Python. You define it, you call fit, you call predict. And then here, it looks like if we look at the mean squared errors, the linear model actually does perform slightly better than the XGBoost model. Now, it's very, very slight, like these are very, very small values here, but something to keep in mind. The best model is going to depend on your feature set. It's going to depend on why you've chosen that model and what problems it's solving for you. And then again, at the end of the day, you might just need to try out different things, different ways of combining your alpha signals together to get the best overall forecast.